Now let's talk about cryptography, which plays a pretty big role in how blockchains work. I mean, after all, it's where we get the name cryptocurrency, and that's going to give you the first clue that, cryptography has a pretty big implications on, why we use blockchains in the first place. So what is cryptography? Well, cryptography really is just the practice of hiding information from other people. And cryptography plays a huge role, in how blockchains work. It determines how the data is secured and decentralized and distributed across the network. And so I'm going to give you a brief introduction onto, how cryptography works and how cryptography is used in various blockchain implementations. This is going to be an introduction. We're not going to get, into all the math about how this works. It gets pretty complicated pretty fast. I don't want to scare you away, but I do want to give you a primer that's going to kind of give you, he's going to give you a framework to help you understand how this stuff works so that you can be a blockchain developer and not necessarily like a mathematician. All right, the first thing to talk about are hashing functions. And these, get used a lot in the blockchain. So what is a hashing function? Well, it's a function, right? So it's a function that takes some sort of input and creates some sort of output, right? Just like any function that you would use in computer science or in programming or anything like that, right? You have inputs and it does something inside the function and it returns an output, right? So the input is going to be some sort of, arbitrary value, like in this case, a bunch of text. And, this text can be run through a hashing function that's going to, do some kind of magic under the hood in order to create an encrypted output, right? It's going to be called a digest. And we can talk about, the properties of this digest, right? So in this example, you can see all this different text that's getting put into a hashing function and it outputs this digest, which is encrypted. So what are the properties of this hashing function and what are the properties of this digest that it outputs? Well, all of the output from this hashing function has a fixed range. So no matter how much input is, inserted into the hashing function, the digest is always the same length. So if you put the word fox in, if you put, the red fox jumps over the blue dog, all of the digest, no matter what the input is, they're the same length, okay? So it's also deterministic, right? So every time we put the word fox in to this cryptographic hashing function, we get the same digest, right? So that makes these hashing functions reliable. Every time fox goes in, the same digest comes out. So we know this function is going to work the same way every single time, right? So another property is that they're discontinuous. What does that mean? So that basically means that even the slightest difference in the input will, basically create a completely different output. Like it won't even look anywhere close to the same. So if we just change one letter, if we turn this to, fog instead of fox and ran the function, it's not like, this C would only change. Like we would get, a digest that looks something like this even, right? Just not even close to the other output of fox, okay? So they're also non-invertible. So that basically means that the input fox cannot be run the other way through the function or even really be derived from the output. So it's safe to look at all of this and you're going to have no idea about how to get the input fox, right? Or if you took this this digest, there's no way for you to know how to get back to, the red fox jumps, or the blue dog, right? So that's some properties of hashing functions and also the digests that they create and how they handle inputs, okay? So how are they used in the blockchain? Well, one of the primary ways is that they're used to chain blocks together, all right? So how does that work? Now, if you remember in some of the previous videos, I talked about how the blockchain is created of transactions. And these transactions are grouped together into bundles called blocks, right? Which are chained together to make up the blockchain, right? And each of these blocks has a header which contains a hash. And this hash is basically the hash of the entire block before it, right? So here's an example. Block 11 in this blockchain, right? Here's block 10, block 11, block 12. Block 11 contains a hash of the previous block, right? So basically, if you took all the transactions that are grouped together in block 10 and all the information about it, and essentially, ran it through one of these hashing functions we talked about a minute ago, it creates, this digest output that's a block hash that's contained in the next block in the chain. So block 11 basically contains all of the data from block 10 inside of a hash, right? Okay. And if you think about it, block 10 would, logically also contain all the data from block 9, and block 9 would, contain all the data from block 8, so on and so forth, till you get to the genesis block, till you get to the first block in the chain. So if you think about it, every block has a hash of the entire blockchain, or the state of the entire blockchain, all in a single hash in its header, right? And if you remember what I said a second ago, how these are, discontinuous, if you change the slightest thing, then you change everything. You get a hash that doesn't even look anywhere close to it. And this is part of what makes the blockchain so secure, is that if you were going to try to change any transaction, in any of the blocks, it would completely change the hash in the block's header, right? And the problem compounds across time. If you wanted to go back and change, a transaction in block number 7, you'd have to basically update the hash and the transactions of block 7, block 8, block 9, block 10, 11, so on and so forth. The problem compounds exponentially across time, across the entire blockchain. And that's a huge security feature of the blockchain. As this problem gets harder to do. It gets harder to change transactions. And that's why cryptography is so important into how each blockchain implementation works and what makes the blockchain secure, right? And to make this matter even more complex, each block hash, there's some constraints about what constitutes a valid block. So each block has a difficulty target, and each block has an arbitrary nonce, or like a random number, basically. And these conditions have to be satisfied in order to create a valid block header, or a valid block hash. And those have to be satisfied in order for the block to be mined and for it to be a valid block on the blockchain. So even if you could go back and hash everything, you still have to pass the validity test, which is another sort of security layer to making this very difficult. And this is also kind of talking about the Merkle roots, which we probably won't get too in depth to in this boot camp, but that's just another thing to think about as well. All right, another part of how the blockchain uses cryptography is called asymmetric cryptography, or public key cryptography. This is the same thing. So this is, has a huge use case in blockchain, and its primary use case is for authentication. And that's basically proving that, data on the blockchain comes from a specific user of the network, of the blockchain network. So basically the goal is to prove that, I sent a transaction. So if I send you 10 Bitcoin, I need to verify that it was actually me that sent you the 10 Bitcoin in order to change my account balance, to remove the 10 Bitcoin from my account and put it in yours. So blockchains use asymmetric cryptography to prove that I actually sent the transaction. So authentication on the blockchain consists of a few different components, right? We talk about public key cryptography or asymmetric cryptography being used for authentication. And, these are key pairs, a public key and a private key. And these are two things that a user owns in order to use the blockchain, right? Your public key is kind of like a username on the blockchain, or at least your account is, which is a derivative of your public key on the Ethereum blockchain. And your private key is kind of like your password, right? And your public key, your username is basically deduced from your private key by the network. But it doesn't work the opposite way. You can't deduce your private key from the public key, and that's what makes it secure. So it's safe to show your public key because it's kind of like a username, but it's not safe to show your private key because it's kind of like a password. And your private key is going to be, basically the secret of how you sign transactions and authenticate that it was you on the blockchain, because you can sign transactions that way, and then your public key can be deduced from the signature. All right, so let's talk about how both of these pairs are used in an encryption algorithm to authenticate transactions on the blockchain. So anytime a transaction is sent, they're signed by a user with their private key. So if I want to send you 10 Bitcoin, I have to sign that transaction on the blockchain with my private key, right? And the goal of this is, authorization to prove that, it's okay for the blockchain to update the balances, right? So whenever I sign it, it creates a transaction, and each transaction contains a signature. And this signature is what's used to verify the transaction. So let's see how that works. So here's an illustration of how public key cryptography works. So in this case, we've got Bob who wants to send a message to Alice, right? So Bob, has this message, "Hello, Alice," which gets encrypted. And this creates some sort of encrypted output, some obfuscated output that's created by using Alice's public key, because Bob knows Alice's public key. It's okay. It's safe. And whenever the message is transmitted in its encrypted format, it's safe. Anyone could see this transmission, and it wouldn't be sensitive. So Alice can get this, and Alice can decrypt it with her own private key, right? So then she can see the original message that says, "Hello, Alice." All right. So that's how that works with the key pairs. Bob uses Alice's public key to encrypt the message. The message is sent, and Alice decrypts it with her own private key to see the message. Okay. So let's talk about how it works in a digital signature fashion, because this is how transactions are authenticated on the blockchain, is with this digital signature. I'm going to sign something with my private key and create a signature that's going to get sent along with the transaction. All right. So Alice actually creates a message and signs it with her private key. Okay. And this message is going to get sent. We're going to see the actual message. The message isn't going to get encrypted. But in addition to the message, we're going to send a digital signature, right? Which is basically just an encrypted version of the message. And whenever Bob receives the message, he is going to verify that the message was created by Alice by using Alice's public key to verify the signature. All right, so let's look at how this works on the blockchain. So anytime I send a transaction, right, let's say I want to send you 10 Bitcoin. I create a raw transaction that contains all the information about how to do that, right? And I send that to the network. But in addition to the transaction, I send a signature, okay? And the signature is basically, what I'm going to do is take the transaction and I'm going to run it through a hashing function, right? We talked about hashes, and it's going to it's going to create some sort of hashed output, okay? And then I'm actually going to encrypt this hash with my private key, right? I'm going to take it and I'm going to sign it with my private key to create a further encrypted signature, okay? And then I'm going to send both the original message or the transaction and the signature. And when it's received to the network is able to decrypt the signature with my public key. And then it's going to be able to take the original message and, run it through the same hashing function and compare the two. And if both of these match, then they're going to know that I sent the message, that I was actually intending to send you 10 Bitcoin. All right. And that's how it verifies that the transaction was sent from me. That's how it authenticates the transaction with this digital signature process, right? So if the signatures don't match or the output doesn't match, then they know it wasn't me. And also, if the content of the original unencrypted message or the transaction changes during transmission, then the signature verification process is also going to fail. So if anything changes, it's not going to work. And that's why we can, send transactions securely on a blockchain. That's how this works. All right, so I know that can be a little tricky to wrap your head around the first time. So, maybe go back and watch this video another time to kind of understand how this works. Like I said, it's not really essential for you to have a super in-depth knowledge of this, but it's good for you to understand, the basics of how these two different pieces of cryptography work when you're trying to become a blockchain developer. So remember, it's the digital signature for this public key cryptography is the primary way that we use asymmetric cryptography in the blockchain, and also these hashing functions are primarily used when you're talking about block hashes to actually chain blocks together and make the ledger secure.